Okay, good afternoon, everybody. So I will talk about electric solar wind sail, which is it's related to the previous solar sail presentation. But in this electric solar wind sail, we actually use not sunlight, but the solar wind as the thrust source. But I will step back a little bit first, so I will talk a little bit more generally. So we have a physical phenomenon which we can call Coulomb drag propulsion, and at the moment there are two application areas for it foreseen, as far as I know. The first one is the so-called plasma brake, which uses which is a way to deorbit a satellite from the low Earth orbit, basically, by using the ionospheric plasma ram flow due to the orbital motion of the satellite. And the second one is, what is the main topic of this presentation, is the electric solar wind sail, which uses the natural solar wind plasma stream for the same for generating propulsive effect in the solar wind. Some words about the theory. So both positive and negative tether polarity would work here, but the negative polarity is limited by a phenomenon called electron field emission from the surface of our thin wires, and that basically limits the negative voltage to around 1 kilovolt. And in the interplanetary application, in the e-sail, we use positive polarity tether because we need much larger than 1 kilovolt voltage, because already the kinetic energy of solar wind protons is about 1 kilovolt, 1 kilo electron volt. And this, so we have a long tether, very long, thin metallic tether, and we keep it at high voltage. And keeping this at high voltage requires some power constantly. And this long tether acts like, in the e-sail case, it acts like a giant Langmuir probe which collects electrons. And therefore we need an electron gun on board which pumps out those electrons back into the solar wind. But the power consumption of that electron gun is relatively low. And then one useful point of this technology is that the thrust scaling is 1 over distance from the sun. So it's not 1 over distance squared, but it's 1 over distance. So the thrust decays slower than with other methods. And that's due to the plasma physics, the dipole length scaling. Here is a particle in cell simulation picture of the e-sail. So basically what forms is a structure which resembles the Earth's magnetosphere, or is a two-dimensional version of Earth's magnetosphere. We might call it the electrosphere, because this is a completely electrostatic structure which forms around this white dot, which represents the charged tether, which is at the middle. And then it took us some time. I mean, this physical principle was invented back in 2006, but it took us some time to figure out how to control this kind of e-sail system in space. So in short, what we can do is that we now have a way of controlling it fully by using the e-sail effect alone. So it means that we can throttle the thrust very easily by just changing the voltage and current of the electron gun. And then we can do thrust vectoring by tilting the spin plane of the e-sail. And this turning of the spin plane is done by differential voltage modulation in synchronization with the rotation of the spacecraft, resembling using an algorithm which resembles helicopter flight. And then last but not least, we can also control the spin rate itself by using the e-sail effect alone. And this is very useful, because otherwise we would have a so-called secular spin rate change in missions where we have to orbit the sun, in missions where we are in heliocentric orbits around the sun. So we have overcome this we can overcome this secular spin rate challenge now by using this kind of special arrangement of the wires, of the tethers. We can also do simpler than that, so we can also have one single tether E-sail for a CubeSat, and then we obtain the useful property that the main spacecraft can do pointing in two degrees of freedom without gimbaling, so without moving parts other than the reaction wheels. And based on this idea, we designed a multi-asteroid touring concept. I will say a little bit more about this in subsequent slides. But first about the tether itself. So the tether is the most non-trivial thing about the of Coulomb rack technology, and the tether is non-trivial because it can't be a single wire, because a single wire would be cut by micrometeoroids very quickly. So we need to use kilometers of long wire, and that is not feasible. The lifetime of such wire would be too short in space. And therefore, the wire must have redundancy. So, and we use fourfold wire, fourfold redundancy. And the technical challenge, which we have only recently been able to overcome, I would say, properly, is how to create these bonds, how to create this kind of fourfold structure. I mean, it doesn't have to be geometrically exactly that structure, but anyway, it must be some similar structure like that. So we create those bonds simply by twisting the wire. So we rely on plastic deformation of the wire and friction to keep these structures in shape in space. So what kind of example missions we can do? So multi-asteroid touring I already mentioned briefly. So we wrote a proposal to ESA back in 2016, and it was also kind of picked up by ESA, but it has also been subsequently developed more. I mean, the details have been worked out more. The idea there is that we send a fleet of CubeSats through the main belt, and you can actually do this by using this E-sail effect. So we obtain a total delta V of like 30 kilometers per second for this mission altogether. And then the key to have a low-cost mission is to return the data at the final Earth flyby. So we don't need to use the deep space network for this mission, and this brings us kind of cost saving. And this is feasible because of the large delta V capability of this system. But of course, the platform must be lightweight, so it's about 5 kilograms maximum of the platform. So one has to miniaturize. Basically, one has to be able to make small interplanetary CubeSats. And then we have been talking about, but this is more preliminary, about a mission which we call North Star, which would be multi-tether mission outward from the sun that would not use any radioactive materials, would be fully solar powered, so potentially a low-cost way of sending small payloads at high speed out of the solar system in such a way that they would stay functional at about up to 30 AU, very roughly at about 30 AU distance. And the key thing here is that we make a structure, inflatable structure, which has three functions. It's the frame of the E-sail, it's a parabolic concentrator for gathering sunlight, and it's also a radio dish antenna. And then we can also have, as was also mentioned by the previous speaker, we could also consider off-Lagrange point solar wind monitoring, or he didn't exactly mention that possibility, but anyway, a non-Keplerian orbit, keep a probe indefinitely in some non-Keplerian orbit. We can do that because we are propellantless. And then last but not least, the plasma brake application, for which we have an ongoing ESA project for deorbiting low Earth orbit satellites. And here are some numbers flying fast outward, which is, I suppose, which is the main topic of this session. So I don't go through all those numbers in detail, but the final, roughly speaking, the final result is that a speed like 100 kilometers per second with a 25 kilogram payload or something like that should be within reach if we use like 30 tethers, each of which is 20 kilometers long. And this is assuming like only small evolution relative to the present kind of laboratory prototypes what we have. And I mean, here again, it's noteworthy. I mean, because the thrust scales as 1 over distance, not as 1 over distance squared, we actually can draw benefit from this solar wind propulsion in this kind of cases where we are flying outward from the solar wind, outward from the sun. Here is another calculation which I made back in 2010. We using a little bit different assumptions, and using 60 tethers, so double the number of tethers. But still, I would say, kind of trying to be as realistic as possible in the mass estimates, but not adding any margins. So that was kind of my approach at that time. And so we can actually, in this case, the end result was that we can, for example, have a 25 kilogram payload at 100 kilometer final speed. Or if we want to have 4 times larger payload, 100 kilogram payload, then we get 75 kilometer final speed. So that gives you some kind of flavor, what is the trade-off between the final speed and the payload mass that we can reach. And this about the scalability of the system, so it is not infinitely scalable. So this probably represents almost the maximum that one can do with this technology. The reason is that, I mean, unless somebody evolves better materials than aluminium for the tethers, because when you scale the tether length to 20 kilometers, then you can't go much beyond that, because then you are hitting the conductivity and tensile strength constraints of the tethers. And then you cannot increase the number of tethers indefinitely, because at some point they start to collide. They tend to start colliding with each other due to the undulations small undulations that they undergo because of the solar wind variations. So this is kind of so this technology is not usable for heavy payloads, but it can be used for small and medium payloads. So it should be quite interesting for science missions in particular. So okay, so here is a brief summary. So E-sail, two models. So single tether E-sail has low thrust, but it's sufficient for small interplanetary CubeSats. And that allows pointing of the payload without gimbaling. So, for example, if you make an asteroid flyby, then you can actually track the asteroid during the flyby, despite the continuous slow rotation of the E-sail tether. I mean, the rotation period, by the way, is of the order of 1 hour, so just to give you a flavor of the number. And then the multi-tether E-sail that you must use if you need larger thrust, and that's also good for fast missions out of the solar system. And then, of course, always we do have the potential of having even higher performance if we develop more advanced tether wire materials, such as carbon fibers or something like that. Okay, thank you very much for your attention.